Welcome to another video. In this video we're going to talk about series, and with all the time we spent on sequences, this should be a little bit more understandable because we already really explored a lot of the hardest parts in sequences. How do you take a series and go backwards? What's a series mean? What's it based on? And are there formulas for it? The formulas are going to make the math so much easier for series. You see, here's what a series does. A series adds up the terms of a sequence. So they are not unrelated things that we have. They're not the same. And sequences in general are just a list of numbers, and that's what we have. We can talk about convergence and divergence or things like that. But a series takes those terms and adds them. Now, there's some very interesting things that happen with series, some very predictable formulas that we can prove by proof by induction. We can prove a lot of these things, and I'm going to show you how to do that when we get there and do proofs by induction. That's in a few videos from now. So we're going to be able to prove them. Some very interesting things happen, and especially when we get into some calculus, like calculus 2, we're going to find that you can actually add an infinite series, an infinite number of terms, and get something. It converges. There's some very special cases to do that. We talk about that in some geometric series in just a little while. But some very fascinating things happen. It's really worth our time to understand how a sequence works so that we can understand how a series works so that we can understand a lot about some calculus later and do some very interesting things with it. I won't go into everything that we have, but some very interesting things happen with like pi and e and a lot of these numbers that are transcendental when we view them in a type of series. So here's what a series does and how they work. If you've never been exposed to it before, this is what they look like. What in the world does that mean? A series is just taking a sequence and adding up the terms. So here's what this tells you mathematically. This sigma is a sigma, it's a Greek letter S, and it stands for a sum. Your sequence is right here. If you ignore this, that's just a sequence. In fact, your series tells you where to start and where to end. So your series is built like a sum of a sequence. Could you find the first, let's say, n terms of this? Well, if the series is telling you where to start, this says, I want you to look for your k, whatever this index is. I want you to look for your k. Here's my k. I want you to plug in 1. Okay, I'm going to plug in 1 to this. It's going to give me my first term. Then I'm going to plug in 2 and 3 and 4. And the natural numbers, because it's based on a sequence. You don't plug in like 1.5. You plug in all the natural numbers because it is a sequence. You're just adding or summing it up until you get to that term. So here's what we would do. Starting with whatever this is, it could be 0, it could be 1, it could be anything. Just start with what this is and plug it in. So our first term says replace your index with 1, and then 2, and then 3, until you get to whatever this is. Now that's an n, so we're not going to be able to stop, but we show that we would do this continuously until we reach the n. Notice that the two different letters that we have, this k is the index of your sequence. This n tells you where to stop. Sometimes n is infinity, and it will be an infinite sequence. We get that a little bit later. But most of the time, that is going to be an actual number. So what if that had been 3? If that had been 3, it would be exactly this. It would say you plug in 1, then 2, then 3, then you stop. That is how a series works. It takes these values, starting here, plugs them into the sequence that you know how to deal with, and stops with that term, and then you add it up. So 1, 2, and 3 from our 1, our 2, and our 3. If that had been 31, you do 1, 2, 3, 4, 5, 6, all the way to 31. You plug them in here and you add the whole thing up. Is it possible? Yes. Is it annoying? Of course, because if you have 31 terms here and you got to add them up, that's a lot of number crunching. Are there formulas? Thank goodness there are. I'm going to show them to you in just a little while in this video on how you would do this quickly, very quickly, because there's formulas that allow us to do that, the k squared. So I'll show you those things when we get there, but in general, that's how the series works. I just intended to give you an example on how you'd find the first number of terms. The actual doing of the math and finding the sum While you could do it this way, there's better ways. Most cases, there's better ways. If this was left as n, we would have to show that we continue until we reach whatever that number is. That's an important step to do for a proof by induction when we finally get there. Okay, let's do one that looks a little bit more complicated. It's not going to be all that bad. This says that here's your series, here's the sequence on which this is built. So you're summing or adding the terms of this sequence by starting at 0 and ending at n minus 1. How do I end at n minus 1? You just plug in n minus 1, just like we just plugged in n. You just start here, show a few terms, then go, yeah, some stuff happens, and we end here. How do we end there? I took n and I plugged it in and we got that term. We're going to do the same thing. So this says, I want you to start adding these terms of the sequence by starting at 0. So if I start at 0, I can do 2 times 0 plus 1. The next term would be, I'd plug in 1, then I'd plug in 2, then I'd plug in 3. It would give me another term for each of those inputs. This is the 0th term, the first term, second term, third term. You can consider it first term, second term, third term, fourth term, but you notice that you started at 0, so we typically call it that k sub 0, or the n sub 0 term, n sub 1, n sub 2, n sub 3. And where we would end is, take your 2 and plug in whatever that is. If we had just watch this, if we would have had a 3 here, this is where we would stop. We would plug in 0, 1, 2, and 3, and we'd be done. That's it. That's all we would stop. Or right where we'd stop. That's all we do. But if you have an n minus 1, then you're going to go, okay, I'm plugging 0, and then 1, 2, 3, 4, 5, 6, blah, 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 going for a, right down here, going for a really long time, and then you would have plug in 2, or you have a 2, plug in your n minus 1 plus 1. It's just an evaluation. Like you plugged in 0, and then 1, and then 2, and then 3, and then where you stop. So take this, evaluate it. That would be 2 times n minus 1. You do have to have parentheses. I hope that you see it as a composition of functions. You're just plugging in one number. It's just n minus 1. And you can simplify all this stuff. This would give you 1 plus 3 plus 5 plus 7 plus, look at what this does. This would be 2n minus 2 plus 1. Wait a minute, 2n minus 2, because I distributed, plus 1 is 2n minus 1. Isn't that exactly what we got for odd numbers in the last video for sequences? Yeah, that's it. And this is really interesting because if you notice this, you can define odd numbers 2 different ways. You can define them by, what if I started at 0? Well, then I would have to have 2 times 0 plus 1 to get 1. What if I started at 1? Then I have 2 times 1 minus 1 to get 1. You can define them 2 different ways. And some of these series and sequences can be done that way. This defines odd numbers the same way that this does. If you think about it, and you want to do it on your own, I'm not going to spend a lot of time on it, but if you think about it, this is going to give you exactly the same thing that this does. Exactly. Plug in 1, 2 times 1 minus 1 is 1. Plug in 2, 2 times 2 minus 1 is 3. Plug in 3, that would be 5. Plug in 7, that would be 7. Or sorry, plug in 4, that would be 7. Plug in n, you get 2n minus 1, 2n minus 1. Same stuff. So this does teach something. This says that you can manipulate one series into being something else by altering where you start and where you stop, and it might even change your sequence that you're working with. So I hope that makes sense. I'm trying to teach you some pretty advanced things just by looking through a couple of examples here. So in general, a sequence, a series, it's just a sequence added up. The sequence is given to you. It tells you where to start. It tells you where to stop. Those can be finite numbers in which you have a finite number of terms, or they can be left as n minus 1 in which you have an infinite number of terms and you just show what that last term is by plugging in or evaluating your n. That's all that series do. In general, we're going to see that there's some formulas that would solve all of these things for us very nicely and let us add up the terms of your sequence without having to do a whole lot of writing out, because this is annoying. And if you went to 50 terms, that'd be crazy. That would take you so much time. We have a better way. All right, another thing that we can do is we can go backwards on a series like we went backwards on a sequence. We can build a series from a sum. And so we're going to show that. It is the same exact technique. So if you have not watched the sequence video on how we build a sequence from a list of numbers, you need to, because we're going to do the same thing here but quicker. So how we do this, the same exact idea is take whatever you're given and write the terms down. So we have 2, then -4, then 8, and those are being added. The next term, think about what the next term would be. The next term would be, let's see, 2, -4, oh wait, it's not 6, it's 8. These are not just even numbers because I'd skip one. 2, -4, 8, the next one would be -16. So if you remember, what we're trying to do is we're trying to make all of these the same form and then figure out the stuff that's not changing in it, and then relate it back to our n, our index. Now there is one other thing here. This series stops. This series does have something, some number as a stopping point. So we're going to have to figure this out. We're going to figure out what that k is, because we're going to write our series and have a finite number there. We're going to figure out what that is. Actually going to be 8, but we'll figure out what that is as we go. So we're going to have to relate it back. I'll do a different example, like if you weren't given that, how you would do it, how it would change. But this is the way we go through it. We list our terms out, then we try to make them all the same form. What do you mean? Try to make them look like they have the same stuff and represent the stuff that's the same as unchanging things in your series. So I'm looking at this going, hey, I have a negative here, and no negatives here. I'm going to relate this to a -1 eventually. So I'm going to say this is -1 times 4, 1 times 8, 1 times 2, -1 times 256. So I know that there's a 1 in there that's not, a -1 in there that's not changing. My exponent will be changing. We talked about alternation, so we're going to have that in our series. The next thing I do is look at our 2, 4, 8, and 256 and try to relate them to the same thing, something that's not changing. Now, this is not even numbers, so it can't just be 2 times something, like 2 times 1, 2 times 2, 2 times 4, 2 times, that doesn't work. But they are all powers of 2. So this is 2 to the first, 2 to the second, 2 to the third, 2 to the, you have to figure that out, but it will answer that question for you. So 2 to the first, 2 to the second, 2 to the third, 2 to the eighth. The next one will be a -1 times 2 to the fourth. And now we're ready to start making the jump for our series. So I know it's being added, so that says we have a series. I know I have to start at 1, and so we're going to have this case of 1. So I know that our first term is going to be our first term in this series as well. I now need to start representing all of this stuff that's not changing, just like we did a sequence. Why? Because a series is based on a sequence. You need to have the same exact sequence. So our sequence should have a -1 in it. Our sequence should have a 2 in it, because the -1 and the 2 are not changing. What is changing? The sign of the first of our terms, our -1 to a power, that's changing. So the exponent here needs to model that. Well, let's take a look. Our first term is positive. So if our first term is positive, it needs to take -1 to some power and give me +1. It needs to take -1 to some power for a second term and give me -1. The way we do that is we take our k and we subtract 1. Now, please get this. Why k and not n? K is the index for a series because you show where you end at the end. You want to be able to plug in that n and get your general term. And so we have to have a different index. We can't use n and then plug in n to the n and represent a different n. That doesn't make any sense. So you start at K and you go, okay, K is my index. That way I can plug in 1 and 2 and 3 and 4 and 5 and 6 and 7 and 8 and end at my n. I can plug in n later and it actually makes sense. I just need like this dummy index and we call it K. Hopefully you're okay with that. So plugging in 1, let's just double check this. Negative 1 to the 1 minus 1, 1 minus 1, 0. Negative 1 to the 0 is 1. That works. 2, I have a 2 in every single one of those terms. And now we relate the other part that's changing, 1, 2, 3, 8, back to my index. It appears that 1 and 1, 2 and 2, 3 and 3, my index is matching. And so this is going to match my index. Again, it's K, it's not N. You can't do that because you're going to end with an N. You can't say that N equals 1, and then 2, and then 3, and then end at N. It's not correct form. You'd have too many N's floating in here. You use a different index, we call it K. Now the last thing, how do you know when you end? Because all of this stuff, you could have just had this and got this. So I'm going to say two things. Number one, if you were not given this last term, let's pretend that wasn't there. If you weren't given that last term and you didn't have this information, you would just put N and you would be done because you would be able to represent that series and you would say it has no end to it. So this, and this, that would give you 1, negative 1, 1, 2 to the first, second, third. You'd have negative 1 to the K minus 1, that matches our signs. 2 to the first, second, third, that matches our index. The first term would give us positive 2 to the first, that's what we got. Second term, when we plug in 2, I'd get 2 minus 1, that's negative 1, 2 to the second, that's what we have. The next term, if I plugged in 3, I would get 3 minus 1 is 2, negative 1 to the second is positive 1, 2 to the third, that's exactly what we have. And we say, if we were not given an end, you put an N there. And that N says you go forever until you reach an N. Do you see how you could write? Remember, we're imagining that's not there. You could write the same series that we have here, and your ending term would be, let's see, 2, negative 4, 8, then negative 16, then blah, 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 and you would plug in N, and you get negative 1, N minus 1, 2 to the N. That would be your nth term. That'd be your general term. That's why we use two different letters. K for your series and the sequence that the series is based on, and then N to represent your nth term, because you need a different variable to plug this into. It's inappropriate to plug an N into an N. You're kind of switching variables there. We want to show that. We don't want it to be ambiguous. Now, we don't have a general term. We have an end. So what's very nice about this is because our index matches our power, index matches power, index matches power, index has to match that power. It's got to be an 8. And it says, oh, okay, if this has to be an 8, then you know that's the 8th term. If you know that's the 8th term and it's the last term, you've just found where you end. This series is represented as, here's the sequence. We know it's right. We've just spent like an hour-long video finding sequences. We know that represents a sequence. We know it starts at 1, and now we know it ends at 8. That is the 8th term. And this is how you would represent that series in series notation. Hope that makes sense. Hope you're seeing the relationship between the sequences that we already talked about. Now we're just kind of relating it back to the sum and showing that a little better with some different letters. Again, we need those different letters because you need an N to be able to plug into something. And we need to end with an nth term, a general term in terms of n, so we need a different variable to base our sequence on. That's the only reason. What we're going to do now is I'm going to show you the formulas for how to add series, because we don't want to be doing this with a calculator or something. I'll show you that, and then what we'll do is practice a couple. Okay, so how do we actually calculate the sum of these series? We don't want to actually write it all out and do it, because that'd be crazy. I want you to imagine something, because we're going to do this problem and you're going to find out that it's not as bad as it looks. Right now, this looks horrifying. Why? Because if you had to actually add that series, what would you do? Well, let's look at it. This series means sum of what? This sequence. It is a sequence. It's based on an index K of 1 to 12. So you do this. You plug in 1, figure it out. Plug in 2, figure it out. Plug in 3, figure it out. Plug in 4, 5, 6, 7, 8, 9, 10, 11, 12. All 12 terms, you'd figure that out, and then you'd add that. That's a lot of work. And we're going to do something that's still a lot of work, but quicker work. Also, hopefully you can tell, I kind of enjoy this stuff. I don't know why. It seems like some sort of a puzzle. I really enjoy it. Don't know why that is, but this is one of my favorite things is the sequences and the series. I like the challenge in it, I suppose. There are some formulas that are going to help us solve series, how to add the terms without having to actually add the terms. Now, you're going to ask the question, where in the world does this stuff come from? One of them is very common sense and needs no proof. Same thing as that one. But the rest of them would require proof. We prove most of these by induction. If you want to know where they came from originally, you could ask someone like Carl Friedrich Gauss. Well, you can't, because he's dead. But if you could, he solved that by himself in like 5th grade, or the level of 5th grade, which is insane. He did it in like, I don't know, a couple minutes, because he was super genius. But anyhow, a lot of these were discovered by pattern and then proved with induction. And so I will show you how to do that. There's other ways to prove it, but I'll show you how to do that in the last video in this little kind of sub-series that we have on sequences and series. So here's what this means. Here's what the formulas look like, because at first they look a little confusing. I'm going to do this one last, actually, even though it's the most basic one. I'm going to do this one. So how you can add up the terms of a series without actually doing the addition is with a formula like this. Now, I want you to understand how this works. This says, let's suppose that your sequence is based on just k. What's it mean? That means that you plug in 1, 2, 3, 4, 5, and that would be the terms of your sequence. 1 plus 2 plus 3 plus 4 plus 5, if you add it up, would create a series. You'd stop at n. So if this was 10, here's what this would mean. This series would be add 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. That's what that would be. Now, you can do that pretty quickly on a calculator, but this is actually even quicker than that. Here's all you need to know in order to find the series, find the sum of that series. Quickly, just know where you end. This is the second reason why we need different letters here, is so that you understand that this is based on the end of this series. So if I'm adding the series of the sequence k from 1 to n, I just take my n, I plug it in here, and it's going to give me the sum. So if I go from 1 to 10, and I know it's based on k, then I just plug in 10. 10 times 11 over 2, 10 times 11 over 2 is 55. That's going to add to 55. If you take your calculator right now, do 1 plus 2 plus 3 plus 4 all the way to 10, it's going to be 55. Why? Because this actually works, and it's provable. I'm not proving them now because I haven't taught you induction, but I will prove that one to you at a different time. Now, there's some other ones. Why are there other ones? Because not everything can be simplified to just having a sequence of k. What about k squared and k cubed? We have 2 other formulas for that. Now, there are other ones out there, but these are the most common ones. So what if you had a sequence based on k squared? Well, what you would need to know is that you're starting at 1 and that you're ending at whatever, like 10 or 12 or whatever that number is. Because if we have that, there's a formula to add it. So if we were ending at, let's say, 7 or something, so we knew the sequence was k squared, we're starting at 1, we're ending at 7. Take your ending number. 7 plus 1 is 8. 7 times 2 plus 1 is 15. 7 times 8 times 15, and then divide by 6. That will give you the sum of 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, and 7 squared all added up. It will do it for you. It's pretty fascinating. Same thing works here with k cubed. If you know where you end, take your ending number, plug it in, and it will solve it for you. Now, what if you don't know where you end? Then this is still relevant, but it won't give you a finite number. There are some infinite series that will, but they have special names like geometric series, and there's special conditions like you have to have a ratio of less than 1. Common ratio. So there are some special conditions, or between -1 and 1. There's some special conditions there, and there's some other series that have the same type of things going on. So, but in general, to add a series, you need to know where you end. Otherwise, it's going to go to infinity. Do you see that? Like if you just kept on adding this forever, and k was numbers 1, 2, and 3, and 4, it's going to go to infinity. Like it's going to get really, really, really big. Even going from like 1 to 12. If this was 1 to 12, so you'd add up 1 cubed, 2 cubed, 3 cubed, 4 cubed, that's already big. 5, 6, 7, 8, 9, 10, 11, 12, all cubed, and you added them, we can do the same thing by taking the ending number, let's say 12. 12 times 13 divided by 2, 78, square, and then square that, whatever that is. Well, that's going to be pretty big. I can't do that in my head. I was trying, but that's a little outside my range. So this is what the formulas do and how they work. They'll add the terms of your series very quickly. Very cool. Now let's look at this one, because this one confuses a lot of people. They go, how do you get the n? Where in the world is that coming from? I want you to think about it this way first and then see that that makes sense. So one thing that we can do is we can say, if you have a constant in there, nothing would change. There's no k in there. So what this would be, this would say, plug in 1. I can't. There's nothing to plug into. So what that would do is say, for the first term, take 1. For the second term, take 1. For the third term, take 1. For the fourth term, take 1. For the fifth term, take 1. For all the terms of the edge, just take 1 and add them up. So if I went from 1 to 7 of the sequence 1, here's what it would do. It would take 1, 1, 1. I wish I would have picked a smaller number than 7, and then to write 7 ones. 1, 2, 3, 4, 5, 6, 7. Here's the first term, it's 1. Second term, 2, 1. Third term, 1. Fourth term, 1. You're getting that back. Fifth term, 1. Sixth term, 1. Seventh term, 1. And then I end because it terminates. It says I end at 7. The seventh term, not plugging in 7. You're trying to, but it's only giving out 1. It's a constant. What do constants do? They're the same value all the time. So 1, 1, 1, 1, 1, 1, 1. There's 7 ones. What do you get when you add 7 ones? Wait a minute, that's repeated addition of the same number. Repeated addition is multiplication. How many times have you repeated it? 7 times whatever is here. That value got repeated. Okay. What would happen here? You'd have a constant. C would be a constant. There's nothing to plug into the C. C would be something like 1 or maybe 5. Let's say 5. What would that be then? Well, if I went from 1 to 7 of, let's say, 5 now, these wouldn't be 1s anymore. You'd have 5, 5, 5, 5, 5, 5, and 5. 1, 2, 3, 4, 5, 6, 7. The first term would give you a 5. Second term, 5. Third term, 5. It's a constant. Seventh term, 5. Well, how many times have you added the 5? Well, there's 7 terms. 7 times 5 would be 35. This is where that comes from. It says take your constant that's not changing. See how many times you have it repeated. Every time from 1 to n. There will be n repetitions of that constant. The other way that you can view this, and this is why it says or, is this, and it's quite important. You can always take a constant being multiplied by something inside of your series and move it in front of the series. So you could do this. You could say, this is the same as, same thing as k equals 1 to n of c times 1. Because c is a constant, I could make this c times the series of 1 to n of 1. This would be c times, we already know that this piece is n, c times n, that proves that to you. So we do get that out of it. We'll see that working through our one example that we're going to get, because I've involved everything of every one of these formulas in that. So we'll talk about what you can do when we get there. Right now, I just need you to be really, really clear on these formulas actually work. They're very relevant, and we're going to use them in just a minute. This one makes sense, but you really have to think about it a little bit. Okay, so back to our example. We don't really want to plug in 1 through 12 and add them up, because that's really annoying, and we have some formulas that do this for us. So the couple things that I need you to know in order to be successful at solving that or adding up that series, finding the sum, without writing it out, is that you can separate series by addition and subtraction and multiplication. Now get why it worked on what I showed you. If a series means addition, adding stuff up, and addition is commutative, doesn't matter the order in which I add stuff, it's also associative and separable, which means that I can add stuff separately and add it back together later. Okay, what does that mean? That means I can look at adding these things and these things and these things and these things up separable, and then, or associative grouping, and then add it back together. So, and long story made short is I can separate by pluses and minuses. I can separate my series into several different series by pluses and minuses. I can move constants in front, factors in front of my series. Why? Because we know that you can factor out the same thing being multiplied in every single one of your terms. Addition and subtraction is factorable by multiplication. So I can take multiplication and factor it in front of my series. It is factorable because addition and subtraction is factorable by multiplication. So in other words, I can break this down in some really simple pieces that match up what we have here. So we're going to do that. We're going to say, all right, because addition and subtraction is it's associative, it's commutative, I can move stuff around, I can separate things, it's also factorable by multiplication, I'm going to start separating this. I'm going to separate it first by addition and subtraction, and then pull my factors out. So I can consider one big series to be a sum of little series. Adding up different stuff and then adding together is the same thing as adding up all the stuff at once. What we're trying to do, our goal, is to get the insides of every one of our series to look just like one of these things. You'll notice that you have to keep the same starting spot and ending spot. You'll also notice I'm not doing a whole lot of work in my head. It's way too easy to start making little mistakes on this, like forgetting signs or forgetting fours, or if you want to be smart about it and go, well, I know I can separate that, but I can pull the 4 out front. That's true, but sometimes we just lose the 4 or make a sign error. So I never do it. That's up to you whether you want to. I prefer to write this stuff out. So this series can be represented as 1, 2, 3, 4 different series because I had 1, 2, 3, 4 different terms, and we can break that up and we can associate it, group it by addition and subtraction. So k cubed, okay, minus 4k squared, got it, plus 5k, cool, plus 7. You'll also notice I'm keeping the subtraction and the addition, that's fine. We want to make sure that we do understand what's going to happen later, though, that I'm subtracting whatever this gives us. That is important. Now, there's some more work that I have to do. I need to make sure that the insides of these 4 series, separated by the 4 terms that I had, match up with one of these formulas I've given you. So we're going to do that. This is great. K cubed is done. We love that. We're going to have a formula for that in just a minute. In fact, it's going to use the 12 that I referenced. I'm going to be putting, for this one term, this one series, I'm going to say this starts at 1. That's what I wanted. This has a k cubed. That matches perfectly. That's the sequence for that mini series. And then it ends at 12. 12 is going to get plugged in here and here, and I'm going to square whatever, I think it was 78 that I said. 78 squared is what that is going to be. We're done with that one. This one, not so much. So this one says I have very close to what that says, but there's a 4. That 4, because that 4, man, I hope you see it. That 4 would be on every single term in the things that are being added. It's factorable. You could factor it out of every term, right? That means you could factor it and move it in front of that stuff that's being added. It's factorable. That means you can move that 4 out front. Hope you're also seeing why I'm not giving you lots of different examples. This pretty much covers everything that you do except for one example, which I'll show you in just a minute. Same thing here, you could factor out a 5 from every one of those terms, so we can move our 5 in front just like a factor does. This k squared is what we're looking for. This k is what we're looking for. And now the constant you can do one of 2 ways. It doesn't matter to me which one you do. You can leave it as this, or you can write it thinking of it as 7 times 1, you could pull out the 7 and leave the 1. Either way, I need you to see that you need the same thing. If you leave it as a 7, you do 12 times 7. That's what that says. Leave it as a 7, a constant. You would do n, 12, times 7. No problem. If you do it like this, you say, all right, if I am adding up lots of 1s, how many 1s am I adding? 12. You're n. You're 12. So you'd say, here's 12 times 7. Either way, you're going to get 12 times 7. It doesn't really matter. What matters is being able to separate this into our number of terms gives me number of series. Then making every one of those series look like something we have a formula for, and then applying the formula correctly. So the formulas are all based on your n, where you end. Your n is where you end your series. I know that sounds similar when I say it. So our k cubed says there's a formula for that. It's right there. So I'm going to take my ending value, my n, I'm going to plug it in. My ending value, my n, is 12. So I'm going to apply this formula and say that this part is 12. 12 plus 1 over 2 squared. This is exactly what that should be. I should take my n, plug it in appropriately, and then we're going to do the math a little later. Minus 4 times, keep that 4, don't lose it. Remember, that's being multiplied by whatever you get out of this. This sum is represented in this expression that we're about to write, but 4 gets multiplied because that is the factor you factored out. Now, because this is based on our k squared, it says find your ending value, your n. Here's our k squared. Here's our formula for k squared. Just plug in your n. 12, 12, and 12. Our n is 12. A good question would be, will you ever get fractions out of this? Nope, they'll all work out to whole numbers. So if you're getting a whole lot of fractions, you're doing something wrong. Those fractions should simplify. So we have a 12, 12 plus 1, and 2 times 12 plus 1. That's coming from our n. Then we do our plus 5, so we have a plus. We have a 5. And then we look at the formula for that series. Since it's based on k, we're going to go, all right, we have an n of 12. I'm going to plug in 12, 12 plus 1 over 2. Lastly, no matter what you do, you'll get 7 times n, which is 12, or 7 times 12. Either way, you're going to get 7 times 12. And we've already talked about why that is. You're welcome to plug that in just like that on your calculator and get whatever it is that this equals. You can also, you're welcome to simplify this stuff however it seems best to you to do. I'll simplify because I don't have a calculator handy. I would do things like this. I'd simplify all of my fractions because they all will. So this is going to be 6 times 13 squared minus, this would give us 2 times 4 is 8. So 4 times 2 is 8, 13, 25. This is going to give us 6. That would be 30. 5 times 6 is 30 times 13 plus 84. That's probably what I'd plug into my calculator. I might double check it to make sure that I did everything right. But I'm going to come back with the answer here, the sum, in just a bit. Okay, barring any little mistakes that I've made, I could have, I don't know, I haven't really looked back at it yet. But if I've made any mistakes, then they should be small errors. But if I haven't, then that is the sum that you get by adding up the 12 terms of that sequence. And that's exactly what you should get there. You can try it, I suppose, if you really wanted to, but that's what you should get. So I hope I've made it make sense as far as how to manipulate a series into something that's manageable by the formulas that I've given you. I'm going to give you one more example about how to manipulate something that doesn't match this. Like, what if you don't start 1? What if you start like 4? I'll show you how to do that. All right, so what do you do when it doesn't match up with where you're supposed to start? Like if you start at k equals 4 and you're supposed to start at k equals 1, is this going to work? No. And don't try to make it work the way it is right now. It will not work. So let's be smart about it. What if it was a 1? Like, could you make it work if it was a 1? If it was that, it'd be fine. We could say, yeah, okay, I know that matches perfectly this. I know what the formula is. I know I'm ending at 24. Like 24 plus 1 over 2, and then take that and square it, and you find the sum of this series. Very quick and easy. The problem is that this is not what this is. So, what is this compared to this? Let's think about what I don't want out of this. I don't want the first term, I don't want the second term, and I don't want the third term in that series. I do want the 4th, 5th, 6th, 7th, 8th, 9th, and 10th. So here's how we can think about it. This series is the same thing as taking the whole series that formula needs and removing the first 3 terms. I hope that you see what this does. This says, here's my whole series. What don't I want here? I don't want terms 1, 2, and 3. This is terms 1, 2, and 3 of that series. So we can always really do that. If you don't start at 1, take the whole series and subtract off starting from 1 to all the stuff that you don't need. So up to, but not including that beginning index, that beginning term. So hopefully that you can see that actually does work. That should kind of make sense. You just have to start at 1 in order for these formulas to work. Otherwise, you're going to start subtracting things, and this is the way that we do it. You know, I want from 4 to 24. I want the whole thing, but I don't want the first 3 terms. That's the first 3 terms. I'm not going to work that out for you. You can easily do that on your own. I just want to show you that's the process we're going through. So I hope it made it make sense. I hope now that sequences and series aren't a huge mystery to you. I hope that you can see they're very manageable. We even have some formulas for series that really, really help us. So we're going to start talking about specific sequences and series over the next 4 videos. We'll talk about arithmetic sequences, then arithmetic series, geometric sequences, then geometric series, and finally, how to prove some of these formulas with proof by induction. So I'll see you for those videos, and I hope you're doing well.